Hello students, welcome to series of lectures on linear integrated circuits and applications. So in this video, I am going to explain first and second order active high pass filter. In the previous video, we have already seen the low pass filter and also its analysis, and we have also seen that the frequency response of the second order active low pass filter. Now let us focus our discussion on active high pass filter. So let's get started. So these are the two important lecture learning outcomes of today's video. We will be able to understand the op-amp basic active filters, and we will be able to analyze the operation of second order active high pass filter. So this is a pin diagram of IC 741. In each and every PPT I am putting this pin diagram to understand it. First order active high pass filter. So what is an active filter? An active filter is a type of filter which includes one or more active circuit components such as op-amp. And coming to the high pass filter, if an active filter permits only high frequency components and which denies all other low frequency components, then it is termed as active high pass filter. Alright, so this is the circuit diagram. Okay, this is the circuit diagram of active high pass filter. This is the first order active high pass filter only. Okay, and you can clearly see from this circuit is that we have given this RC pair to the non-inverting input of operational amplifier. Okay, so obviously what is the pass band gain? The pass band gain A is equals to 1 plus Rf by R1. That's all. Okay, so a first order active high pass filter which is a composite of only one reactive component capacitor accompanying with an active component of one. So let's recall the concept of the low pass filter. In the low pass filter, the first component is the resistor and the second component is the capacitor. But here we have interchanged the passive components. That is, the first component, input component is the capacitor, and here the output component is the resistor. That is only the change, and the remaining everything is same. Alright, so this is the first order active high pass filter we have analyzed. So the overall voltage transfer function, that is V0 of S by VA of S, that is gain into input, that is 1 plus Rf by R1 is the gain. Input is nothing but the voltage divider rule across this resistor. You will be getting RSC by RSC plus 1. Okay. So for in steady state, when you consider S equal to J omega and all, and you will be, so this is S is equals to J omega, and you will be getting what? Omega L is equals to 1 by RC. So which is the lower cutoff frequency for high pass filter. So this is the voltage gain. We will be getting A0 by 1 plus J FL by F. And if you take the magnitude, and we'll be getting A0 by under root 1 plus FL by F whole square. So this is the magnitude response we'll be getting from this equation. Okay. Alright. So these are the two important observations we need to identify. The first observation is that for frequencies very much less than FL, the gain will be 0. For frequencies equal to FL, the gain will be A0 by root 2, and the frequencies more than FL, and the gain will be equal to pass band. And this is a observation that we have made according to the equation that we have already seen in the previous slide. Okay, what you need to understand, for frequencies far less than FL, the gain is 0. Okay, and recall what we have already discussed in the case of low pass filter. In the low pass filter, for frequencies less than FL, FH there, the gain should be maximum. Here the gain should be minimum, that is 0. That is only the case we are going to be observing in the two responses of the filters. Okay. So if you want to plot the graph on a graph sheet, you will be getting the pattern should be like this. For frequencies F less than FL, the gain should be 0, and for frequencies F equal to FL, the gain will be 1 by root 2. So this is the point, 1 by root 2, and for frequencies F very much greater than FL, and the gain will be equal to the pass band gain. So this is the pass band gain. Okay, this is the pass band gain and this is the stop band. Okay, so that's pretty much about this active high pass filter, that is first order. Alright, when it comes to the second order active high pass filter, so the second order active high pass filter and the second order active low pass filter are almost the same, because for the analysis purpose we are considering admittances, that is Y1, Y2 or Y3 and Y4. Okay, instead of taking directly resistor and capacitor. And we also demonstrated what benefit we are getting if we consider admittances in place of the resistance and capacitors. Okay, but only the thing, the difference here is that So here y1 is the capacitor, y2 is the resistor, y3 is the capacitor, y4 is the resistor. That is what the difference. Whereas in the case of the second order active low pass filter, the reverse. Y1 should be resistor, y3 should be capacitor. Okay. So please you do the analysis, because we already done the analysis part of the second order active low pass filter, and one expression we have got. So up to that expression, every step is common here also. Okay, the step is very similar, the way how we already developed in the case of the active low pass filter. Alright, so at last you will be getting the transfer function should be like this. This is very important. That is h of s is equals to a naught into s square by s square plus alpha omega l square omega l square. Okay, and if you common omega l square, you will be getting this expression. Okay, and from this expression also we are in a position to calculate whether it is providing the response of the active high pass filter or not. Okay, so here we are going to be taking the two important observations. Okay, so in this expression, if you substitute s equal to 0, what will happen? Okay, and s equal to infinity, what will happen? So that these are the two important considerations we are going to be taken into consider in order to see whether it is providing the high pass frequency response or not. Okay, so let us get started now. So if you substitute s equal to 0 in this equation, what is happening? This is denominator term, that is omega something by 0, which is infinite. Okay, here also infinite. Infinite plus something is infinite. So something by infinite is 0. So that is the reason we will be getting h of 0 equal to 0. Okay. So if s equal to 0, h of 0, the response equal to 0. This is the point that we already analyzed. That's the first one. Okay. And what is the second point we need to observe? If you substitute s equal to infinity, alright, what will happen? If you substitute s equal to infinity, something by infinity, which is 0. Okay, here also something by infinity, which is 0. 0 plus 0 plus 1. This is overall, we'll be getting 1 in the denominator. That is a naught by 1. So what is the total response? We'll be getting a naught. Okay, for s equal to 0, h of 0 equal to 0. For s equal to infinite, h of infinite equal to a naught. Okay, so therefore you will be getting what? This is 0 and this is a naught. Okay, so obviously if you connect the dots here, and you'll be getting the pattern should be just like similar to the frequency response of the high pass filter. Okay, and what is FL? The lower cutoff frequency FL is equals to 1 upon 2 pi RC. So which is same as in the case of the low pass filter. There is no change at all. Okay, the way how we are taking the component values. So that is only the difference. Okay. So under steady state condition as s equal to j omega, the voltage gain magnitude equation of the second order Butterworth high pass filter can be obtained. So Butterworth filters, I clearly mentioned in the class also, all audio filters are Butterworth filters. Okay. So the second order Butterworth high pass filter that can be obtained as a naught by under root of 1 plus FL by F whole to the power of 4. Please understand, this is the power 4. Okay. And for nth order also you will be easily calculate. The generalized transfer function that can be written as h of j omega by a naught, which is equals to 1 upon under root of 1 plus FL by F whole power 2n. If the order is 2, the power will be 4. Please understand. If the order is 3, the power will be 6, like that. Okay. So this is the generalized transfer function for nth order active high pass filter. This is very important. Okay, right. So this is the circuit diagram of the second order active high pass filter. Okay, right. So for low pass filter, you should consider resistor and capacitor. For high pass filter, you should consider this is capacitor and this is resistor. This is capacitor and this is resistor. That is only the difference. Thank you, students. Thank you for watching this video.